Good afternoon, ladies and gentlemen. Today I'll present a chapter of my dissertation entitled Measuring the Importance of Traffic Road Segments. Traffic road segments are the links between two nodes, one origin node and one destination node. If you take a look at this map of Metro Manila, these white lines represent the links. Some people call these links segments or road segments, and some people would call these arcs. In this particular chapter of my paper, what we try to do is to estimate the degree of congestion on each road segment by applying SPCP. SPCP is the shortest path counting problem, which I will discuss more in detail later. So to start with, let's talk about congestion. Whenever we talk about congestion on a road segment, especially in Metro Manila, we always imagine traffic congestion. So whenever we have traffic congestion, it means on a particular road segment, the traffic volume is very high. Why is it high? Maybe one reason is that that particular road segment is very important, very popular. That's why it's very congested. However, in this particular study, what we will do is to estimate the degree of congestion without using traffic volume data. Because as we all know, traffic volume is a little difficult to obtain, traffic volume counts. So what we will do in this particular study is to estimate the degree of congestion without using traffic volume data by applying SPCP. SPCP is the shortest path counting problem. To give you an idea of what SPCP is, I'll give you the computational procedures. For SPCP, the step one is to find the shortest path between two nodes. So for example, in this map of Metro Manila, for example, from this node to this particular node, there are many possible shortest paths. You can go from this place, go around this way, and so on, but there's only one shortest path. So for the SPCP, step one is to compute for the shortest path between two nodes. Step two of SPCP is to compute all possible shortest paths in the network. So given this Metro Manila network, or given any other network, step two would be to compute all the possible combinations, the shortest path between all possible combinations of origin and destination nodes. And step three is to count the number of times that each road segment is included in the shortest path. So given that we have computed, for example, in step two, all the possible shortest paths, so there will be some shortest paths which should be included in other shortest paths of different origin and destination nodes. So what we want to find out is which road segments are always included in the shortest path. To give you a clear idea of the shortest path counting problem of SPCP, I'll give you a very simple example. So this is our example. So this one, the circles represent the nodes, so the letters are the nodes. And then these lines will be the links, the road segments, the arcs. And these numbers represent the distance. For example, the distance from node A to node B is 5 kilometers. From node A to C is 9, and so on. So to review the SPCP procedure, in SPCP, step one is to compute for the shortest path between between two nodes. For example, let's compute the shortest path between node A to node B. There are many possible combinations. You can go straight from A to B. You can go around from A, D, G, F, C, and D, and so on. So there are many possible combinations of paths. What we want to find out is the shortest path. And the shortest path in this case would be the one from A to B. And it only has a distance of 5. Next, how about looking for the shortest path between node A to node C? The shortest path between node A to node C, there are many possible combinations again. We can go straight from A to C, from ABC, from ADC, from ADGC, and so on. But in this case, the shortest path from A to C is going from A, B, until C. Why? Because as we can see, the total distance is only 5 plus 2 is only 7. For example, 7 kilometers from node A to C. And then the next part is we compute the shortest path between node A to D, the shortest path between node A to E, and the shortest path between node A to F. And lastly, we also compute the shortest path between node A to G.